Alright, so today we'll be talking about linear regression. Up until now, we have basic idea about what machine learning is. So we got to know that there are three kinds of machine learning: supervised, unsupervised learning, and reinforcement learning. Supervised learning is the one which is guided. Just a moment. Unsupervised learning is the one that is not guided, and reinforcement learning is the one that takes help with the means of reward and punishment mechanism. Okay, so here the data it is labeled. Okay, well labeled data. Here the data it is not labeled. So and here we just have an agent who is working in an environment and with the sole purpose to maximize these rewards. So these are three kinds of learning, types of machine learning that we got to know about. Also, machine learning is the study that is associated with making predictions by analyzing data. Okay. We also got to know about two different kind of problems that are very prevalent in machine learning. So we know that there are regression problems and also classification problems. Now, if my we have like two kinds of variable here, we have x and we have y. With this x is the independent variable, and this is our target variable upon which we have to make some kind of prediction. So this target variable of continuous nature, the problem will be that of regression. If the target variable it is of categorical nature, means that computations cannot be performed. So there are classes such as 0 or 1, yes or no. Or we also took an example about leave or not leave the company. So when there are categories, and these categories there can be more than two. So it's necessary that I'll have only two categories. I can have more than two categories. So if this y variable target is of continuous nature, categorical nature, the problem will be of classification because then we we need to predict that to which class our y variable belongs, whether to class 0 or class 1. Correct. So let's talk about linear regression today. Linear regression, as the name suggests, this is a regression problem. So you guys can very evidently see that there are two words which is forming this term, linear and regression. So regression means that this algorithm is concerned with predicting a y variable which is of continuous nature. Okay. And linear means that this algorithm it assumes that there is a linear relationship between x and y. So x that is my dependent variable and y that is my dependent variable. They are linearly uh, related with one another. Now, what do we mean by this linear relation? So let's take an example. Let's say that I have a data here, and we very well know that height and weight they are directly proportional to one another, which means that if height is increasing, weight also increase. If height decreases, it also decreases. So this is kind of a linear relationship. If I have some heights and weights, so let's say these are the heights and these are the weights. So I might have 160, 175, 165, 162. And let's say the weight is 55, 68, and 58, and 54. Okay, so these are the weights. Okay, random assumptions I'm taking. So for majority of data, for majority of observations, this relationship it holds true. Okay? Like height is directly proportional to weight. Height increases, weight also increases. You might have few cases where the height is increasing and the weight is not increasing. So those cases, they can be termed as outlier. But if it like talks about the major data, so we know that the data is going to follow this particular relationship, right? So if I plot, like if we're going to plot this data that we have for height and height, this plot, it will look somewhat like this. Yeah. Okay. Let's say I have height on x-axis and I have weight on y-axis, right? So this is kind of relationship, it is termed as a linear relationship. And linear regression, it is used, it models a relationship. It assumes that x and y, they are linearly related and y is of continuous nature. All right. So this is the algorithm that we use if the data that we have, it is linearly related x and y, and the y is of continuous nature. This comes under supervised learning. Okay, so this is the first algorithm of supervised learning that we are going to study. Now, this part is clear to us that this is a linear relationship and this is the data that we have for which the relationship is it can be modeled as linear. But how we are going to make predictions and what kind of predictions are we going to make? So here, if I ask you that this is my data, okay, and if I draw a best fit line for this data, can I use this line as a medium to help me predict for X height what is the weight? Since this data it shows a linear relationship, and if I model this data and I draw a best fit line from this, I can use this best fit line as a medium to tell me for each X what is the weight, right? So okay, here, if I have an unknown weight, so this is my data. All the green crosses, this is the data that I already have. And this red point, this is an unknown height. So this best fit line, if it perfectly models all of my data points, I can make it as the median, and this will tell me that for this height, what is the weight. Okay, so this is how predictions are done in linear regression. You draw a best fit line for your data, and for this best fit line, what do you do? It is going to help you to like figure out for any unknown height what is the weight. But how to draw this best fit line? Like there can be a number of lines that can be drawn between these data points. So firstly, let's also establish this linear relationship here in the data that we have. So we know that height and weight, these are directly proportional to each other. And if I like remove this constant of proportionality, I have to like if I have to remove this proportionality, I have to replace it with a constant of proportionality. So here in this case, let's call it n. Okay. So for a value of height that I want to predict, if I have the weight and if I have the value of n, I can predict the height. Right? Can you guys give me a thumbs up? Can I write this? If height and weight, they are proportional to one another. And if I remove this constant, this proportionality symbol, then I have to replace it with a constant of proportionality. Let's say it is m in this case. So for every value of m, so I can assume that m is 1 or m is 0.8, like few values of m I can assume, and I can plug in the weight. I can like plug in this weight in the equation. So like for first case, m is, we are assuming that m is 1 and weight is 55, and we can like predict the height. So the height is 55, which though it is wrong, but we have made some kind of predictions, right? Now you guys can see that not always this value of m will correctly predict uh, like what is the height. So I need to add a bias, or I need to add like some amount of error that can occur. So what do? We modify this equation as mw plus c. Can I write it like this? Can you please give me a thumbs up if I can write it like this? Okay. And this equation, it somehow seems familiar because this is the equation of a straight line. Okay, I can write it like y equals to mx plus c. And which kind of straight line is this? This is my best fit line that will help me to make prediction. This line. Okay, so this is what? This is my best fit line. So now if I want to predict any target variable y that is of continuous nature, and I have this value slope for the best fit line, and I have x, which is weight in my case, and I have the intercept, y-intercept of the best fit line, I can easily calculate height, right? So theoretically, it is possible to make any kind of prediction. So what do we do? Like we can establish the different values of m and different values of c. Like so for different values of m and c, I'll get what? I'll get a different prediction. And if m is different, it means that this line, since we can draw n number of best fit line in this particular area. So if m and c, they are different, so it means that there is a different line. Basically, these are the parameters that will help me draw a different line between these points. Okay. So if I change m and c, the line will also change. But there can exist only one best fit line between these data points. And can you tell me what a best fit line is? What do you mean by a best fit line? Yes, guys, what is a best fit line? So one thing about best fit line, it may not necessarily pass through. And I am specifically saying that it may not necessarily pass through all the points. But it should be like passing uh, like all the points, all the data points. They should be somewhat near to this best fit line. Now, if this is the data, okay, and instead of drawing a line, I draw a curve like this. Now, if I compare it with the best fit line, this curve, it should be more suited to make the prediction. But why we are drawing a best fit line only? Why not a curve that passes through all the points? Since a best fit line, it won't necessarily pass through all the points. So why not draw a curve and why only the line? So this is a very important problem that can occur in machine learning model if instead of drawing this fit line, we draw this curve that is passing through all the points. So here, what could be a problem that might be easy? See, this data that I have plotted, okay. So whenever we are drawing some kind of representation, so that representation we cannot easily calculate from the curve. Okay, yeah, one point is that we cannot easily make calculations from the curve. For the best fit line, we have this equation that we can follow. But there is one important term or one important problem that arises if instead of best fit line, we make this curve. So I'm telling that whenever I'm plotting the data, this data, it is part of my training. Okay. Because this best fit line, it is helping me to train my model to make some predictions. So these data points, they represent my training data. Okay. Now, if instead of drawing the best fit line, I am drawing this curve. This curve, it is fitting my training data perfectly. Okay. Like you can see that for this value of this is weight and this is height. This value of weight, this is the height, right? But if I take any point from random, let's say this is my point, and here I am testing this specific line. So for this unknown point, the prediction that it is going to make, that prediction it might not be correct. Okay. So this problem, when we like fit a curve that is passing through all the points, this problem of overfitting. There are two kinds of problem, overfitting and underfitting. This problem, it is called overfitting. Let's understand this overfitting with help of an example. Let's say I am making a data, I'm making a machine learning model which is going to predict whether an object is ball or not. Okay, so this simple prediction, my model is going to make. To train the model, I provide some parameters, and the parameters are that if the shape equals to round, right, then it is what? It is a. So this is parameter that I provide. Now this is my model, and I'm feeding this model a data, and the data is that I have what? I have a cricket ball. No. Okay. So for this cricket ball, the model is going to make correct predictions. Okay. The prediction would be correct because what is the shape? The shape is round. Let's say I have another object which is somewhat round. And just for the sake of example, I'm going to take an apple here. Okay, let's consider that the apple, it is like almost round, or you can consider any other object. Right now, I can only think of apple. So this apple, it is somewhat round. And since my model, it has only one parameter, that is of shape. It is also going to say that this apple, it is not an apple, and it will predict it to be a ball. Okay. So here, what is the problem? That since the data is trained on very less samples, and the parameter, there is only one parameter to make the prediction. The predictions are not correct enough. So this problem, it is of it is of underfitting. Okay. Now, if I change this model and let's say I provide the shape equals to round, and there is also diameter. Diameter equals to let's say 10 centimeters. And we also have a property, and the property is bounce. Now, this is how I have modified my model. Okay, so here if I feed a ball, so the shape is round, the diameter is 10 centimeter, and the property is bounce. Let's say this is the case, less than or equal to 10 centimeter, and the ball is, it is a cricket ball. So this would be treated correctly as a ball. If I pass an apple here, so the shape round, diameter is also less than 10 centimeter, but the property of bounce, it is not present in apple. So the model will predict that this is not a bounce. Now, instead of passing a cricket ball or a smaller ball, I pass a basketball or a football. The shape is round, the property of bounce is also there, but the diameter, it might be more than 10 centimeters. So to basketball as well, the model says that this is not a ball. So here I have provided features, but still the model is not making correct predictions. This is the problem of overfitting. Overfitting means that we have provided so many parameters, so many features, and the model is hugging those features. Okay, so it is hugging the training data, and that's why it is not able to make correct predictions on the testing data. So this is what is happening over here. And that's why instead of drawing a best fit line, we do not, we like never, ever, we draw this kind of curve because this is going to overfit our data. Here, the model it is trying to like imitate, it is trying to learn from every information that is present inside the data. And this is also like some kind of over learning is happening here. So it is like trying to model a relationship between height and weight depending upon each and every data point. But we do not do that. We want a best fit line that is able, that is appropriate, and that can pass from all of these points. And basically, that would be helping me to make correct predictions for an unknown height. What would be the weight? Now, I realize that this is a lot to understand, but do you get the crux of it? Can you please give me a thumbs up if you understand a little bit of what linear regression is? Okay, now let's take some data and let's understand linear regression. Let's see how this plotting happens step by step. So let's consider that I have x and I have y. Value of x is 1, 2, 3, 4, 5, and y is, let's say, 3, 4, 2, 4, and 5. Okay, so this is the data that I have over here. Okay, and what I want to do for this x, I want to predict y. Now, what would be the first step? So the first step would be to like represent this on a graph. Let's see, these are the points that I'm marking. So 1, 2, 3, 4, 5, 6. Okay, and so the first point it is 1 and 3. Somewhat here. Second is 2 and 4. Somewhat here. Third one is 3 and 2. It would be here. Fourth one is 4 and 4 here, and 5 and 5. So let's assume that this one is here. Okay, so this is a relationship between x that is independent and y that is of dependent nature. Now we need to draw the best fit line. So there are some like points that we should keep in mind while finding the best fit line. So we know that this best fit line, it should, this is the equation of the straight line. But we know that there can exist n number of lines between these data points, right? So the first thing that will help me to draw the best fit line is to find the point. So what I'm going to do, I'm going to find the point from where all of my best fit will be passing. So if I draw like n number of lines here, I know that all the lines that they will pass from that particular point. So for this, I calculate the mean of x and I calculate the mean of y. So let's assume that the average value of x here, it is 3. And the average value of y here, it is, let's say, 3.5. Got it? Now, these average. So what I have done, I have calculated the, pardon me, I have calculated the average of x and I have calculated the average of y. And let's say 3 and 3.6. So somewhat here, 3 and 3.5, sorry. Here is this point that is existing. So since, just a moment, let me just correct the markings. Okay, so this is not here. I'm not able to undo it somewhat here. Okay, so this is the point 3, comma 3.5. That denotes the average of x and y axis. So this line, okay, or this point, it can serve as a medium. I am not able to draw a straight line right now. Okay. So this particular point of intersection right here, this is the point from where all of my best fit line will pass through. Why? Because this is the average of my data, average of X data and average of Y data. So no matter how many lines I draw, all of these lines, they will pass through this point. Can you all agree? Can you please give me a thumbs up if you agree? Okay. Now, what would be the second thing? So if I want to predict this Y, I need to have the value of slope and I need to have the intercept for this best fit line. So mathematically speaking, the formula of slope. So second part is to calculate M and calculate C. So firstly, let's calculate slope. So to calculate slope, the formula that we use, it is x minus x mean multiply by y minus y mean divide by x minus x mean whole square. And we sum all such values. So for this data that we have over here, I'm going to calculate x minus x mean. Okay, then y minus y mean for all the observation, y minus y mean, and x minus x mean whole square, and x minus x mean multiply by y minus y mean. And I'm going to add all these terms together and put in the formula. Can you confirm the formula of slope? This is the formula, right? Please give a thumbs up if you can confirm that this is the formula. Schools, we would use this to calculate slope. All right. So this is going to give me the slope. And let's say for this data, the slope, it comes to be 0.4. Okay, I'm assuming this value. Now, the second thing is to calculate intercept. So we have the equation, right? Y equals to mx plus c. And we have just calculated the slope for this data that we have. So at like I can plug in m here, which is 0.4, and I still need y and x. But since I know that all of my best fit lines, they will pass through this point, that is 3 and 3.5. So what I can do, I can calculate the intercept plugging in these x and y value, which is 3 and 3.5. So let's do that. Y equals to 3.5, m equals to 0.5, x equals to 3, and we can calculate intercept. All right. So I know of this. Yeah, delta y divided by delta x, change in y and change in x. That is slope. Okay, so for this data, this is the formula that I have used. Okay, so like we are calculating the change of each and every observation, how far each and every observation is from the mean. And similarly, we are calculating it for y as well. And then we are dividing it by the difference between the observation of x and the mean. This we are doing, I'll tell you why we are using this particular kind of formula. Just give me a moment. Okay, so this is going to be giving me intercept, and the intercept would be what? Intercept, let's say it is 2.6. Okay, this is the value that we get. So now we have the intercept and we have the slope. And in our data, we also have the values of x. Okay. So we have x, we have slope, we have intercept. Can we predict? Like this is the equation that we have found. M equals to 0.4, C equals to 2.6. And let's say for first observation of xi, it is x equals to 1. And I want to calculate y predict. So whenever you want to like calculate y predict, the representation is y hat. And for it, if I'm going to calculate, so uh, 0.4 x plus 2.6, I can plug the value of x here. So this is going to be 0.4 into 1 plus 2.6, which is going to be roughly equals to 3. So this is what I get. I get y predict here. See. And this is the y test. So I'm going to match and I'm going to compare whether the prediction that are made, these are correct predictions or not. So similarly, I can plug in all the values of x in this equation and I'll be able to get some kind of value for y. Let's say these are the values. Okay. Till here, do you guys have any doubt? How we calculated slope, how we calculated intercept, and how we plugged in the values in this particular data? We have like successfully calculated the y predicted. So now this particular y predicted, this y hat, it has been calculated by fitting data on a best fit line that has a slope of 0.4 and that has an intercept of 2.6. But if I want, see, I can change these values of slope and intercept and I can plot another line. And for that line as well, I can calculate, let's say, y dash hat. Again, that line will give me some predicted values. So in the same manner, I can like change these values 10 times or 20 times, and I can calculate various values of y hat for different best fit lines, for different lines, not the best fit line. The best fit line is always. So once I get these values, once I get for different lines, I get what? I get different values of y. Now I want which is my best fit line from this data. So what can I do? What can be done to like plug out your best fit line from these multiple lines? So we know that each and every line will give us some y hat, and we already have the value of y. So according to the data, this is the truth value, and this is the predicted value. If I calculate, if I perform the difference of these two, like the actual value minus the predicted value, I'll get the loss or the error, right? So for all the lines, n number of lines that you are trying to fit between this data, you are going to calculate the difference between y and y hat. So this is what? This is the actual value and this is the predicted value. And which data? This value is going to be what? This is going to be minimum. That is going to be my best fit line. Can you please give a thumbs up if you understand how to identify the best fit line from all the lines that we are going to cover? To identify or to like represent this loss, there is a parameter, not a parameter, that there is a concept that is called R square. So we have R square, we have adjusted R square. There are like various kind of matrices that will help you to find which is the best fit line. For now, we'll understand what R square is. So there is a simple formula again. R square is y predicted minus the average of y divided by the summation and y minus y. So here y bar it is the average of y data that you already have, basically average of all the truth values. Yp, or you can also represent it as y hat. It is what? It is the predicted value. So what you are going to take, you are going to subtract each and every predicted value from the average. You're going to square all such averages because they can be negative as well. And you're going to divide it by the uh, like by subtracting each and every truth observation of y from the average. So this is the formula. Now, one thing that can pop in everyone's head. Do we have to like memorize all of it? Like we have studied a lot with regards to only one algorithm. This is like linear regression only. and there is so much maths involved. So do you like have to cram it or do you have to memorize it all? No. We have Python, and Python helps us to implement all of these things very easily. And that's why, like, whenever we talk about implementing machine learning algorithm, Python is the first choice because the implementations, they are very easy. You don't need to worry about what would be the slope, what would be the intercept, the algorithm, the functions that Python has. They will themselves calculate it and they will give you a line. For that line, you can use another function to calculate R score. If the R score is less, since this is telling you the accuracy of the line, if it is less, what you can do, you can train your model again. Okay. If it is more, if the accuracy is more, you can do what? You can like stop the training. Okay. Please give a thumbs up if you understand the whole crux of linear regression. Okay. So one more thing before we start the implementation part, linear regression, it is of two kinds. There is simple linear regression and there is multiple linear regression. And the equation that we have studied, which is y equals to mx plus c. This is the equation of straight line. But when we talk about the equation of linear regression, that is also same. But if you search for it, you will find it written in somewhat fancy manner. What is the fancy manner? Y equals to alpha x plus. This is how you will come across the equation of linear regression. And for that matter, equation of simple linear regression. Simple linear regression simply means one thing that y, it is dependent only on one variable, only one means. However, multiple linear regression means that y, it is dependent on several independent variables. So there can be n independent variables. Okay. So with respect to multiple linear regression, the equation changes a bit. So we have alpha 1 x1, alpha 2 x2, to alpha n xn plus beta. Okay. So this is the equation of multiple linear regression. Please give me a thumbs up if there is no doubt related to what regression is, how the algorithm works, what is the maths behind it. All right, just give me a minute and we will start with the implementation thing. Let's take a break. All right. Do we have everyone here? Please give a thumbs up if everyone is present. Okay. One more thing. Again, this is the equation. for simple linear regression and multiple linear regression. You you have to remember one thing that this equation of simple straight line, it is the crux or it is the soul of linear regression because you can see various representations of this formula across the internet. So you can also find it written like this, like y then beta naught plus is beta 1 x1 plus beta 2 x2 for n values, and there might be some kind of error that is also added. So here this is your intercept, these are your slope coefficients, okay, and x1 x2, these are your independent variables. So there can be like various ways to write these equations, various representations. So don't get confused by it. It is not that there are multiple equations for it. The equation is only one. Okay, but people can write it in different ways. So sometimes instead of beta, you will also find like beta naught plus beta 1 x1 and beta 2 x2 like so. Okay, so don't get confused by it. All right, so with this, we have successfully understood what linear regression is. Let's understand the implementation as well. So for implementation, I'm going to take a simple data and let me also just drop that data set for you if anyone is willing to code. Just a minute. Yeah, the data set is in the chat box. If anyone is willing to code along, they can use the data set. So I'm going to start the implementation by importing pandas and numpy, and we will also plot our data. So from matplotlib, sorry, Sklearn dot linear model. So Sklearn is the library, linear model is the module, and we are going to import the linear regression function. Right. So the imports are made. After that, we are going to import the data set as well. So this is the data set advertising.csv. You can see that this data set it contains some columns. We have TV, radio, newspaper. So these are the information about the money or the uh, cost that is invested to conduct TV ads, radio ads, or newspaper ads, and how did they affect the sales. Okay, so sales here is the target variable, and we have this data. I call it ad. Okay, mm, now in this data, like firstly we can try and check if there are any null values present or not. So is null and dot sum. So the data is cleaned. So only one step of pre-processing I have done, which is to check whether the data there is any null value or not. But you have to carry out all the steps to like scaling and normalizing, and encoding. Right now, this one does not require encoding. And check for duplicate values. The data set, it is like not that large. Only 200 values are available. So mostly the data is cleaned. You won't find any kind of duplicacy or inconsistency in the data. But when dealing with large data, please make sure that you carry out all the data pre-processing steps. Now, talking about, let's understand what are the columns which are necessary for us. So if I want to predict sales, I first need to check whether sale, what kind of relationship is there between TV and sales, radio and sales, newspaper and sales. So this column that is unnamed, it is of no use to me. Okay, in nowhere in my model training I'll require this column. So it is better that we drop this column. What is funny? Just let me copy. Okay, so the column is dropped. You need to specify the values for access. Otherwise, by default, the drop function it searches and rows. So you need to specify that you need to remove this column from the access one, that is the column. In case equals to true means so that the changes they get reflected in your original data set. Column is now removed. Let's try to understand the relationship between the X column and the Y column. So we have the ads, we have radio ads, and we have newspaper ads. The target column it is sales. So I'm going to see, firstly I'll see just for TV. Is there any kind of relationship between TV and sales? So let's draw a scatter plot for that matter. TV on the x-axis and sales on y. Let's also be available to the station. TV ads, PLT, y label. Yes. And let's do PLT dot show at the end. You can see this is the scatter plot that we have. Clearly, a linear relationship exists between TV ads and sales. So, like if I invest more in TV ads, my sales will be affected. I might like increase my sales. So far, this is an important relationship between the data. Let's try to predict based upon TV ads. Let's try to predict the sales. So if there is a company which is willing to invest in TV ads, they can get an idea that what amount should I invest for a particular kind of sales. Got it? So what we need to do, we need to now fit the data to the regression model. So here we'll be creating a model. Now, one thing that you should keep in mind is that here I am implementing simple linear regression, right? Because there is only one dependent variable that independent variable that I'm considering for now, which is TV, for which I'm going to predict sales. So in this case, this is a simple linear regression model. So firstly, I need to like split my data, and splitting means train, test, split. Use some part for training and reserve the other part for testing. So to do that from SKLine or model selection module, we are going to input name test split. This is the function that will allow me to split my data set. But before splitting, I should also define which is my X variable and which is my Y variable. So can you tell me which is X and which is Y here? According to the terminology that we have been discussing so far. Please tell me which is X and which is Y. X is TV, Y is sales. So let's let the TV column, the data for TV in X, and let's also get the data for sales in Y. If I show you what X and Y are, it is X, and this here is my y. Okay. Now I need to divide x and y into train and test. So we will be generating four things: x train, y train, x train, x test, y train, y test. So these are the four types of data that this train test split function will generate, and the order will also be same. So like if I run it, this is the train test split. I have to provide the value of x and y. I have to provide the test size. Test size means what? How many data, how much part of the data I want to reserve for test and how much I should be using for training. So ideally, I told you that you can use 80% for training and 20% for testing. Feel free to like use several kind of variations of this ratio, but ideally it is suggested that 80% and 20%. So I'm going to define here that my test size is going to be 0.2, which means out of my data, 20% is for testing. There is also a third parameter that is called a random state. Because the train test split function, it will generate. When you run it again, a new training and testing data will be generated. So this happens by random. And if you want to fix it, you use this random state parameters as any kind of integer value, and then the train test split function will be fixed. And no matter how many times you run it, the data will be same. But if you want that, you want to carry out training multiple times. So you can like remove this parameter. So each time that you run it, you'll get a different data. Please observe the data at first record. So right now we have 14 and 2 4.1. If I run it again, the data exchanges. Okay, let's fix random state for now. And now observe the data. How many times the data stays the same. Now you guys can also observe that this gives me a list. And this list it contains several series. So how to identify which thing is what here? So if you read the document and you go to the bottom, here in return type you'll see that this is the order in which you'll be getting the data. You'll get X train first, then X test, then Y train, and Y test. Okay, so I can assign these variables. And now X train, it has the training data for X. Y train, it has the target value for the training. And if you check the shape, this is extreme dot shape and lightning dot shape. You check the shape for X test and Y test. So you guys can call that there are total 200 records. And I decided that 20% is going to be my training. So X test and Y test, they have how many? They have like 40 each. And in training, we have 160 for X train and 160 for Y train. Please give me a thumbs up if you guys understand everything till here. There is no doubt. All right. Now the very next thing is to like create a model for linear regression. So what do you do? Use the function that we have imported and you create an object of linear regression. And upon this object, you will fit the data. So linear dot fit. This variable, this object name. Okay, so this is a variable, it can be anything. Here I'm going to pass my training data. So X3 and Y3. Okay, we are getting some kind of error. All right, yeah. One more thing that you should keep in mind, the model, the function for linear regression, whenever you fit it, it will always require the data, okay, the training data. and basically the x-ray and y-ray of two dimensions. And currently you guys can see that the data that you have x-ray and y-ray, if you do printing, it is one dimensional data. So here in simple regression, you will also carry out one extra step, that is reshape the data. In multiple linear regression, you do not need to do this because you'll have various values of x and it will be anyways two-dimensional. So here we need to reshape our data. So what do? We'll get x3, and it is better that if we do it before splitting. Yeah, let's do it here so that we don't have to do it multiple times. And in the bottom, where I get the errors, you can see that the recommended shapes are these. Either I can use -1 or 1, or I can use 1 cross -1. I'll tell you what is the difference between the two. Right. So currently, let's understand how the shape will change. This is the shape of my data. So what I have done, I have got all the values out so that it resembles an array now. Currently, it was a series. I have like got all the values out. And since this is an array, I can apply the reshape function. You guys can see that this is a one-dimensional array at present. If I use reshaping as 1 minus 1, this is a 2D array. Okay, 2D array, and the shape of the array plot is 1 cross 200, 200 columns. But this is not the shape that I require. So I'm going to try another technique that was mentioned in the error. So minus 1 cross 1. Here, each and every feature is now a separate row inside my data. If you check the shape is 200 cross 1. And this is what I want to achieve. Upon this, my model will be working perfectly. So simply just replace this part. And similarly, we have shapes as well. We are going to use the reshaping technique. Minus 1 cross 1. And let's rerun all the cells again. Okay, so now you can see that the model it has perfectly fitted. Now let's do one more thing, and what we are going to do now. This has given us, since this has fitted the model. It should have whatever line it is using, whatever is the best fit line. That line should have a slope. That should have an intercept. Right? So we need to know the values. We need to know what are the values of slope and intercept with the best fit line for this particular model. So what you can do, you can basically use this regression object and you can use an attribute that is 4f underscore. And this gives you the shape. And if you want to know the intercept, this is the attribute that you can use, and this gives you the y-intercept or the best fit line. Yeah. So do you understand how you can get the coefficient and intercept for this line? If you want to calculate the score, that is the ask. So you can use the coefficient again, and you can use the score functions. Pass your training data. Since on this data you have created the model, so you're going to like predict the score for this data. It is 0.639, which means the it is pretty good. Okay, though it is not like the score, it is not a 1. If it is 1, then the fit is perfect. But like it is a nice fit. For now, we can consider that. So let's use this line to make some predictions now. So we can use predict function on this object, and you can pass X test. So for this X test, you will get some observation right here. And this is why predicted. And can you remember that we also have whitelist? This is what the model has predicted. And these are the actual values. I mentioned it here. Predicted. And these are the you can plot the predicted values. So we'll be seeing that how to plot the predicted values and how to see the best fit line. And you can also like represent them one beside the other and in a data frame. So let's create a data frame from this for the C. So I'm going to use the data frame function. I pass a dictionary. I call it that this is the predicted value given by predict. And these are the actual values which are stored inside my test. Okay, we need to convert them into 1D again because data can will accept only one-dimensional data. So one thing is that we can flatten the data. Okay. So this is by test. Yeah. So here you guys can see that these are the predictions that my model made. And these are the actual value for y. So for 23, it made a prediction 17. For a value that was 16, the prediction was 16.77. All the prediction you can see. You'll be also able to observe that the predictions, they are not perfect. And well, you can see that the accuracy, it is also not very high. It is okay. So for that, these are the predictions. All right, please give a thumbs up if you understand it. Okay, now let's represent the predicted data and the actual data by the means of a chart. So I'm again plotting the scatter plot for PV and scenes. Let's give it a color. And I am going to plot the predicted data with the help of, you can use a scatter plot here as well, but I'm going to use a line plot so that we can get a best fit line of this data. Like here, we pass why I predict that color can be, let's say, blue. Just a moment. X and Y must have shape 214. Yeah. So this is the data. So these big data points, these are my actual values, and these are my predicted values. That you guys can see with the help of a line plot. If I simply change kind from line to scatter, you can clearly see that these are the values that the model has predicted. Here I have passed X test, and for X test we have what? We have permanent. You can also show Y predicted and Y actual with the help of a scatter plot. So here I'm going to like remove this part. So we have X test and and Y test. Okay. So you can see that these pink values, these are my actual, and these blue values, these are my predicted. Not a perfect model, I agree, but here our goal was not to achieve perfection. Our goal was to just see the implementation. We'll talk about how to perfect this model, how to increase the accuracy in the forthcoming sessions. All right. With this, we are going to end the session today. I may understand that this is a lot to take in, but if you divide all of this information and understand it step by step, you'll be able to understand what linear regression is and how to implement it. All right. If there are any doubts, please discuss your doubts. Otherwise, you are free to leave the session.